When a furnace is running, operating conditions have to be carefully monitored and controlled. Operators need to keep an eye on process variables and other conditions and make adjustments to keep the furnace operating at peak. During furnace operation, you'll rely on a variety of instruments to give you the readings you need. Furnace conditions are normally monitored from a control room and from instrument panels at the furnace. One condition that must be monitored and controlled is airflow. Process variables relating to airflow include draft and excess air. Draft is the flow of air and other gases through a furnace, and excess air is the amount of air supplied to the furnace in excess of the theoretical minimum amount required for combustion. A furnace won't perform efficiently if the draft and excess air are off. Draft is often determined by measuring pressure at different spots in the furnace. In this case, there are pressure transmitters that measure draft at the top or arch of the radiant section and at the base of the radiant section, in the firebox, that is, in the area where combustion occurs. Draft may also be measured in the stack, typically at a point below the stack damper. Draft is usually measured in inches of water, and the draft gauge reading should be correct for all of the areas in the furnace. If the draft is positive when it should be negative, the furnace won't perform well, and there's a risk of damage to the furnace structure. Now, excess air readings are based on analysis of the flue gas. In general, this analysis determines the percentage of oxygen in the flue gas, and that percentage gives an indication of excess air. Furnaces normally have draft and excess air targets or acceptable ranges. Operating within the targets can save money in fuel costs. Basically, the airflow conditions in a furnace are controlled by coordinating the positions of the stack damper and the burner air registers. In addition to the airflow conditions, the fuel supply to the burners also has to be controlled. If there's too much fuel, some could be wasted because fuel may leave the furnace without being burned. If there's too little fuel, there's a risk of flameouts and explosions. The pressure needed for proper fuel flow is regulated by control valves. These are the main fuel control valves. They regulate the overall fuel system pressure. In this system, fuel flow to the header is regulated by this control valve, which is called the fireman. Since flow depends on pressure, the fuel pressure is measured. Pressure is typically measured in units of pounds per square inch. In this case, it's pounds per square inch gauge, PSIG. When fuel is burned, it produces flue gases. A process variable that's closely watched is the flue gas temperature. Flue gas and other furnace temperatures are usually measured with thermocouples. Flue gas temperature is often measured in the convection section and in the stack. If the flue gas temperature is too high, there could be a fire in the convection section, or the furnace may be operating above the normal firing rate. An excessive firebox temperature can overheat the tubes and refractory and damage tube supports. So far, we've seen furnace instrumentation related to fuel supply and air supply. Now we're going to look at the process. Two main variables associated with the process fluid system are temperature and flow. The outlet temperature, in a sense, is the most important furnace temperature reading, since the main function of the furnace is to heat the process fluid to a certain temperature. Another temperature that's routinely checked is the tube metal temperature, or skin temperature. Overheated tubes can lead to tube ruptures and other problems. Besides temperature, the process fluid flow rate is also monitored. The fluid has to flow at the proper rate to be heated to the proper temperature. The flow rate for process liquids is often measured in barrels per hour. For many furnaces, both the process fluid outlet temperature and the process fluid flow rate are controlled automatically. You should know how your furnace's control systems work so you can monitor the way they're controlling the furnace. Let's look at a typical example. This system controls the process fluid outlet temperature by adjusting fuel flow to the burners. There's a thermocouple to measure the outlet temperature, a temperature controller, and a fuel flow control valve. During operation, there's a desired outlet temperature or set point. Deviations from set point trigger control actions. For example, if the outlet temperature gets too low, the temperature controller picks up the change and signals the fuel flow control valve to increase fuel flow to the burners. The additional fuel generates more heat, which brings the outlet temperature back to set point. Now, if the outlet temperature is too high, the temperature controller closes the fuel control valve slightly. The valve allows less fuel to flow to the burners, which causes the outlet temperature to drop back to where it should be. For some furnaces, the flow rate of the process fluid is also controlled automatically. These control valves regulate the flow in a 4-pass furnace. Each valve controls 1 pass. There's a set point for each pass. Usually it's the same for each pass. Maintaining the same flow rate allows the process fluid to be heated to the proper temperature more efficiently. If the flow rate deviates from set point in any pass, the control valve for that pass is repositioned automatically to increase or decrease flow and return the flow rate to set point. In this topic, we looked at furnace instrumentation, process variables, and control systems. Now's a good time to try a couple of practice questions on this material. An experienced operator can tell a lot about how a furnace is running by simply looking and listening. During your inspection, it's a good idea to check places where air may leak into the furnace. Air leaks can reduce the efficiency of the furnace and give misleading draft and excess air readings. The inside of the furnace should be looked at too, but follow the necessary safety guidelines. To avoid getting burned, wear a face shield and stand to one side when you open the peephole doors. Inside, the firebox should be relatively clear. If it's extremely hazy, you may not be supplying enough air to the burners. Also look at the condition of the tubes. Bulges in the tubes are warning signs of overheating, and the bulges could lead to tube ruptures. If you notice shiny or bright and glowing sections or silver streaks, these could be indications of hot spots, which are overheated areas of a tube. Also see that tube supports and hangers are not bent or broken. Damaged tube supports can be a sign of overheating and metal stress in the furnace. Look at the refractory too. Its color should be uniform. Glowing areas may mean that some sections of the furnace are getting more heat than others, but dark spots may be an indication of an air leak. What you want is a good heat balance in the firebox. When you inspect the furnace, it's especially important to check the condition of the burners and the flames. Make sure that all burners that are supposed to be operating are doing so. Flameouts invite explosions because unburned fuel can collect in the furnace. Adjusting the burners is a part of furnace operation that gives you direct control of combustion efficiency. Burners may have to be adjusted for any of several reasons. Poor flame patterns, changes in the firing rate or in the type of fuel burned, or even abrupt wind changes are a few examples. Judging a burner's performance can be tricky, but there are some basic guidelines that can help you determine if adjustments are necessary and how to make them. For example, all the burner flames should be about the same size, and the flame should be fairly still, not jumping around. An erratic, sparky flame may be the result of an improper fuel and air mixture, in which case you could adjust the air registers or the fuel flow to the burners. A sparky flame can also be caused by dirty, plugged, or eroded burner tips that need cleaning or replacement. Also, the flame should not be so long that it's impinging on the tubes. Sometimes you can shorten a flame by adjusting the amount of air fed to the burner. The fuel supply can also be regulated to adjust the flame length and pattern. For example, if the fuel pressure is incorrect, the flame could be lifted off the burner, risking tube impingement. An abnormally high fuel pressure could lift the flame off the burner. Therefore, decreasing the fuel pressure corrects the problem and brings the flame back toward the burner. If the fuel pressure is too low, the flame could burn inside the burner tips, producing a whistling sound. Most of the flame patterns and burner adjustments we've seen are for gas burners. Oil burners are operated a little differently. With an oil burner, besides adjusting airflow, another way to manipulate the flame pattern is to adjust the atomizing steam flow. For example, by adjusting the steam flow to the atomizer, you can adjust the length of the flame. The fuel oil pressure to the burner can also be adjusted. If the fuel pressure is too high for the amount of atomizing steam and combustion air that's supplied, the result could be unburned fuel oil. This shows up as a smoky, hazy firebox and smoke coming from the stack. This problem is typically corrected by decreasing fuel oil pressure or increasing steam or air to the atomizer. In this topic, we saw how to inspect a furnace and adjust the burners. Now's a good time to check what you've learned with a couple of practice questions. Checking the draft and excess air can tell an operator a lot about airflow conditions in a furnace. If the readings are normal, chances are pretty good that the draft and excess air are okay. But if the readings are not normal, adjusting the burner registers and the stack damper can often correct the situation. Some airflow problems, however, can't be solved by simple burner and stack damper adjustments. One fairly common problem is an air leak. If air leaks into a furnace, it can lower the temperature of the flue gases inside. An air leak can also lower the temperature of the tubes and the outlet temperature of the process fluid. If this happens, the temperature controller will call for more fuel to bring the outlet temperature back where it should be. Since more fuel is needed, the cost of operating the furnace goes up. An air leak can also throw off the excess air readings. For example, an air leak can cause the excess air value to increase. So a high excess air reading may mean that there's an air leak near where the reading's taken. Dark spots on the refractory could also be an indication of an air leak. Leaking air cools the refractory, making it appear darker than the hotter sections. A potentially dangerous airflow problem is insufficient airflow at the burners. If there's not enough air at the burners, some of the fuel sent to the furnace may not get burned. With unburned fuel in the furnace, you may notice that the firebox is hazy. Also, since the fuel is not burning completely, the outlet temperature of the process fluid could go down. If the outlet temperature goes down, the outlet temperature controller will trigger an increase in fuel flow to the burners. But this only aggravates the problem. If this extra fuel doesn't get burned, the outlet temperature is going to keep dropping. Besides the drop in outlet temperature, the insufficient airflow can lead to another problem. If air in the furnace reacts with the unburned fuel building up in the furnace, the fuel may ignite away from the burners. This ignition may produce a positive pressure in the firebox. The positive pressure further impedes airflow into the furnace, making the original airflow problem even worse. This could cause even more unburned fuel to accumulate in the furnace. In addition, the positive pressure may cause flames to shoot out of the edges of the peephole doors or other furnace openings. Also, the igniting of fuel away from the burners may produce a pulsing or thumping sound. If this airflow problem is not corrected, the burner flames could go out. Eventually, there may be so much fuel built up inside the furnace that if there is an ignition, it could literally blow the entire furnace apart. To correct this problem, first you may need to take manual control of the furnace and start cutting back on the fuel flow to the burners. When the fuel flow is reduced, the haze in the firebox should start to go away. Then the stack damper and the burner registers can be adjusted in small increments to meet the desired draft and excess air targets. A sudden rush of air into an air-starved furnace could cause an explosion, since there may be unburned fuel in a hot environment. We've just looked at airflow problems related to air leaks and to insufficient air at the burners. The next example is actually a combination of these two problems. It's called afterburning. Afterburning can occur when you have an air leak in the convection section at the same time that you have too little air at the burners. If there's not enough air at the burners, unburned fuel gets carried into the convection section. Then if you've got air leaking into this section, it can combine with the unburned fuel and ignite, which could cause a lot of damage. With afterburning, you may see smoke coming from the stack, as well as excessively high stack or convection section temperatures. And since afterburning is caused partly by insufficient air at the burners, you may notice an overly hazy appearance in the furnace. To deal with this problem, you may need to reduce fuel pressure until the hazy firebox clears. Then you can use the stack damper and the burner registers to start adding more air to the burners. In addition, if the afterburning is a result of an air leak in the convection section, the leak should be sealed up and the furnace repaired if necessary. In this part, we'll look at furnace fuel system problems. Fuel problems can arise when the flow of process fluid is significantly reduced and it's necessary to operate the furnace at a lower firing rate. At a reduced firing rate, it may be hard to supply enough fuel to the header to keep all the burners going. To avoid this, the operators may close off some of the burners and their registers so that no fuel is sent to them. When you shut off fuel to some of the burners, The fuel flow to the operating burners will be increased, reducing the risk of flameouts. Firing with fewer burners is a way of maintaining fuel pressure while satisfying the reduced demand. A problem that may occur in gas systems is freeze-ups in the fuel lines. In cold weather, condensation in the fuel can freeze and create problems for the operator. A knockout drum can remove most of the condensation, but a small amount may remain in the fuel that's sent to the furnace. In cold weather, even a small amount can cause a freeze-up. If you do have freeze-ups, you may find them in low points in the fuel system, where moisture can collect and freeze. If this happens, the fuel header pressure may decrease since the ice restricts flow in the fuel lines. Because of the reduced flow, eventually the process fluid outlet temperature will also decrease. In response, the fuel control valve opens up, trying to send more fuel to the burners. Some plants handle freeze-ups by injecting steam into the fuel lines while the furnace remains in operation. The steam thaws the ice. Abnormal conditions in a furnace include problems with the process fluid system. The tubes that carry the process fluid are a potential source of trouble. A common example of a tube problem is a hot spot. Hot spots are overheated areas of a tube. They may be caused by flame impingement or by insufficient process fluid flow. If there's impingement, the fix may be as simple as adjusting airflow to the burner to shorten the flame. If reduced process fluid flow causes a hot spot, increasing the flow rate through the affected tube often works. If there's more fluid moving through the tube, it will carry away more heat. Another way to handle a hot spot is to reduce the firing at that area in the furnace. If the burner closest to the hot spot is turned off, you'll direct less heat toward the problem tube. A hot spot may lead to coking, the buildup of carbon deposits inside the tubes. Coking can restrict fluid flow and cause heat transfer problems. Coking may be detected in multipass furnaces by comparing the flow rates through the passes. The flow rate will often be lower than normal through the restricted pass. The flow rate may have to be increased through that pass to equalize the flows through the furnace. Adjusting flow rates and firing rates are short-term solutions. They'll let you keep the furnace going temporarily until the problem can be fixed. But if there is a lot of coke built up in a tube, it should be removed. Many furnaces have decoking systems to remove the buildup from the tubes. This system injects steam and air through the tubes to remove the coke deposits and carry them out of the tubes. Another tube problem is a tube leak. When a tube ruptures, any flammable process fluid that escapes is likely to catch fire in the furnace. A high stack temperature is one sign of burning process fluid. Smoke coming from the stack is another. When there's a tube leak, you may also see smoke coming from the tube access doors. But if you do, don't open the door. The sudden rush of air could cause a flash fire. When there's a fire from a tube leak, the course of action will depend on the severity of the leak. If the leak is small, you may be able to keep the furnace going for a while. Also, in some cases, the leak will seal itself as coke forms around the hole in the tube. In many plants, the furnace is shut down and the fire is smothered with steam. With any fire, the operators will have to keep a close watch on furnace conditions and follow their unit's safe operating procedures. In this topic, we looked at several abnormal operating conditions in a furnace, including airflow problems, fuel system problems, and process fluid problems. To see how well you understand this material, let's stop so you can try a few practice questions. The pressure needed for proper fuel flow is regulated by control valves. These are the main fuel control valves. They regulate the overall fuel system pressure. In this system, fuel flow to the header is regulated by this control valve, which is called the fireman. Since flow depends on pressure, the fuel pressure is measured. Now, if the outlet temperature is too high, the temperature controller closes the fuel control valve slightly. The valve allows less fuel to flow to the burners, which causes the outlet temperature to drop back to where it should. When inspecting a furnace, look at the refractory. Its color should be uniform. Glowing areas may mean that some sections of the furnace are getting more heat than others. But dark spots may be an indication of an air leak. What you want is good heat balance in the firebox. The fuel oil pressure to the burner can also be adjusted. If the fuel pressure is too high for the amount of atomizing steam and combustion air that's supplied, the result could be unburned fuel oil. This shows up as a smoky, hazy firebox and smoke coming from the stack. This problem is typically corrected by decreasing fuel oil pressure or increasing steam or air to the atomizer. We've just looked at airflow problems related to air leaks and to insufficient air at the burners. The next example is actually a combination of these two problems. It's called afterburning. Afterburning can occur when you have an air leak in the convection section at the same time that you have too little air at the burners. If there's not enough air at the burners, unburned fuel gets carried into the convection section. Then if you've got air leaking into this section, it can combine with the unburned fuel and ignite, which could cause a lot of damage. If you have freeze-ups, you may find them in low points in the fuel system, where moisture can collect and freeze. With freeze-ups, the fuel header pressure may decrease since the ice restricts flow in the fuel line. Another way to handle a hot spot is to reduce the firing at that area in the furnace. If the burner closest to the hot spot is turned off, you'll direct less heat toward the problem tube. A hot spot may lead to coking, the buildup of carbon deposits inside the tubes. Coking can restrict fluid flow and cause heat transfer problems. Coking may be detected in multipass furnaces by comparing the flow rates through